Thank you very much to the organizers for giving me the opportunity here to talk about one really of my favorite topics, that is frequency-agile instrumentation for high-field DNP and EPR. As many of you probably know already, this is also really a little bit of a difficult time because one of our good friends and colleagues, Melanie Rosé, unfortunately passed away last week. And so I'm dedicating that talk to her. You will actually see a lot of references to her work. Because she has this constant driver in like bringing the field of DNP and forward. So with this, I'm gonna start. In this tutorial, I'll do a kind of start with a recap of Gyrotron-based DNP spectroscopy. What are the benefits and where are the limitations? And then I'll add more to about microwave technology, about microwave sources, what other sources are available. And we're slowly kind of going through and kind of building up the spectrometer here. And the one part are transmission lines. And then I'll do a short break, see if there are more questions about these parts already. And then we dive into like how to build a spectrometer, and a very central part of the high field instrumentation, which is quasi-optics. And then I'll show you a few examples of spectrometers that have been built, and it's really, the focus is more really on the instrumentation here, on the hardware. We've seen through all these tutorials already a lot of applications and what you can do, and I hope this is a little bit gives some inspiration to young researchers or old researchers to think in new ways, because even in the 10 years that I'm working now with Bridge12, or the 15 years that I have started in DNP spectroscopy, so many things have changed specifically for instrumentation, and things that were outrageous to think about 10 or 15 years ago are now possible. So with this, let's do a short recap of Gyrotron-based DNP-NMR spectroscopy. So this is a figure that many of you probably have seen already from one of Melanie's articles on describing instrumentation for solid-state dynamic nuclear polarization. And this shows your typical setup of a gyrotron as the microwave source and your NMR spectrometer here. And so you have these transmission line that connects the microwave source to NMR, and then you have cooling here, and some control system for the gyrotron. So this system, commercialized by Bruker, is a turnkey instrument available for NMR spectroscopy from 400 to 900, possibly even higher frequencies in the future. It uses a high power microwave source, and this has truly transformed the field of DNP-NMR spectroscopy. Because you don't need to worry about instrumentation anymore. You can do your, you can perform your experiments. There's still researchers that work with that system will find a lot of flaws still, but in things that don't work out. But it is a huge step towards making DNP-NMR spectroscopy widely available, and also kind of broadening the field from biomolecular spectroscopy all the way to material science. This is a very, very powerful setup. enables kind of a turnkey DNP usage. However, there are limitations to that system, and there are mainly if you're not interested in like straightforward applications, but you would like to use the instrument to develop new polarizing agents, new polarizing methods, then there are some limitations to the system. Mainly because the Gyrotron is a fixed frequency source, there's sometimes some tunability to the Gyrotrons, but really it is a fixed frequency source, and that makes it a fixed frequency spectrometer. Some of the systems are equipped with a sweep coil, but the sweep coil on a superconducting magnet is you have a very limited sweep range. Plus, after all, it's still a NMR spectrometer, so you are concerned about field homogeneity, and so if you start sweeping the field, the main field of the system, then you need to reshim at every field position to get like the really high resolution. So while this is really a workhorse spectrometer, it limits a little bit your ability to study new mechanisms, and it really focuses on the application of DNP. So if we take this apart a little bit and see what are the components of the DNP-NMR spectrometer. So this is a slide that I made long time ago when I was still at a postdoc at MIT, but it still shows all the components that you need to do DNP. You need a probe that goes to low temperature, allows you to irradiate your sample with microwave. You need a microwave source. Here it's a Gyrotron, but there are other sources, and we'll get to that in a minute. You need a transmission line to kind of get the microwave power to the probe, to your sample, and then you need a polarizing agent. So in this tutorial, I will focus mainly on the source and the transmission line and how to get the microwave to the sample efficiently. So you're aware of the Gyrotron now, but there are many other microwave sources available. The microwave community knows a lot of different ones. So here you have the Gyrotrons, you have traveling wave tubes, klystrons, backward oscillators. These are all called vacuum devices because you have an electron beam in the vacuum that you accelerate, and through either going through a magnetic field. This can be an on-resonant or an off, or in the Gyrotron, the frequency depends on the magnetic field strength, whereas in the TWT, you use the magnetic field to kind of focus the microwave beam. So those are all vacuum devices, and they typically are in the higher power regime. And then you have all the different solid-state devices here. For vacuum devices, the Gyrotron is in the DNP community probably the most prominent one, but there are also klystrons, interaction oscillators, interaction klystrons, amplifiers. We have traveling wave tubes. If you run a 10 gigahertz or an X-band pulse EPR spectrometer, you are very familiar with the TWT because this is how this is the amplifier that you're using to generate the power. And then there are backward wave oscillators. However, for DNP, if you need a high power source, the Gyrotron is really the only demonstrated high power source for frequency larger than 263 gigahertz. There's actually in the sister Zoominar, the MIT organized by the MIT group. There's a fantastic talk by Monica Blank about millimeter sources for NMR DNP, and that you can watch. And she goes in great detail about the physics and how the Gyrotron works. It's a fantastic introduction there. So and I got inspired by one slide that she showed in there, which is kind of a comparison of different sources. So we have here the solid state sources, the other vacuum electron devices, and then the Gyrotron. And you see that in terms of size and weight, the solid state sources are the Klystrons, so they're very compact and very small, whereas the Gyrotron, that's a bigger installation. In terms of facility requirements, solid state source, you need an outlet somewhere on the wall to plug the power supply in there, but that's it basically. And for the Klystrons, it's sometimes a little bit more demanding because you maybe need some cooling water and some protection of high voltages. So because the Klystron tube requires high voltage, so you need to be careful with this. The Gyrotron, we know, they're modest, the facility requirements really. In terms of output power, the Gyrotron is really the one that wins here. I mean, 50 watts, that's low power for a Gyrotron. The Klystrons and interaction oscillators, they're like in this 1 to 10 watt regime, still good for DNP. However, the solid state sources are definitely on the lower range. In terms of price, the solid state sources win definitely. They're not cheap, but compared to a Gyrotron, they are very cost effective. The EIK Klystrons are somewhere in between. And there was this line, cost per watt. That was an interesting take by Monica on how to look at these devices. And in this case, the Gyrotron really wins because it's just such a high power source. And for your investment, you have actually a very good investment here. Whereas the solid state source, if you look at cost per watt, it becomes actually quite expensive there. So I add one more line to that, and that's the frequency agility, which for commercial Gyrotrons, I would argue they don't fall into this class of frequency agile sources. There are demonstrations, for example, by the Barnes lab, where you can modulate the acceleration voltage in the Gyrotron to sweep or create basically different frequencies on the Gyrotron. But this is really, I mean, you need to be a Gyrotron expert to build something like this. This is not a off-the-shelf product. However, the solid-state sources are frequency agile, that you can easily sweep the frequency, depends on the bandwidth, and so that is really the source to go. So if we look a little bit at solid-state sources used for or that are available, there's really one key player in the area, that's Virginia Diet, and they're pushing the field forward in terms of frequency and power for like a long for many years already. So this is a graph that I every now and then grab from or that I make from the information that I get from VDI, and just on the website, and see what they built recently. What you can see that here in 2012 it looked something like this here. So If you go up to 350 gigahertz, 400 gigahertz, the power really drops here. There's not much power available here in these higher frequencies. However, the field, their technology has so advanced that continuously over the years, this has pushed to higher frequencies and higher powers. In these systems, the operation is very simple, or it's very straightforward. You start at low frequencies, typically X-band, somewhere in the 8 to 12 gigahertz regime. You have a lot of components available in that area, and they are fairly cheap. And then the amplification multiplication chain is what gets you up to the high frequencies. So they're typically called AMCs, and you will see a few references throughout the talk here. They are truly frequency agile. You can, of course, they have a bandwidth. You can't go from like DC to 500 gigahertz with a device like this, but every dot here represents one certain AMC, and they have a bandwidth. The price, the higher the bandwidth, the price that you pay for is that the typical output power is a little lower. But for all purposes, DNP, a solid state source has sufficient bandwidth to cover the radical that you're looking at. They are cost effective. They have very, very small footprint. These are really very compact systems. And in terms of facility, there's really like, if you have an outlet somewhere, you can run a solid state source. There's no three-phase power, no air, no cooling water required. The limitations, of course, the low power. So what this typically means is, if you look at labs that use these solid state sources, they try to go to the lowest power possible, the lowest temperature possible for the experiments. So keyword there is like helium spinning, and also make the efficiency to deliver the power from the source to the sample, make this as high as possible. So there are what kind of transmission line you're using to connect the source to the power, but also how you couple the microwave power in there. When I was preparing this talk, there were so many things that then later came to my mind that that are missing at the end. For example, coupling to the of microwave to the sample. But this is beyond the scope of this talk, so I'm not going to talk about this. And I hope maybe there's in the future there's going to be a tutorial on that. So can you use solid state sources for DNP? Yes. And again, here a reference to Melanie's and co-workers' work. So you see here, this is a typical amplification multiplication chain operating at 263 gigahertz, can be mounted directly under the NMR spectrometer and irradiate your sample. You get fairly, I mean, these numbers are impressive. Factor 50 enhancement here at 100 Kelvin. This is truly impressive. And it is a combination of like this really short transmission line, but also how to get this, the microwave efficiently into the sample. So I am an EPR spectroscopist by kind of training. This is how my career in magnetic resonance started. So I'm always curious, not only about irradiating the sample, but also can I study the sample, the EPR properties. With this system, you see this is excitation only here. So you don't get any information back about the EPR spectrum. And so I am now looking at possibilities in in the rest of the talk now to see how can we also detect the signal that comes back from the sample, and not just the irradiation. So kind of my dream DNP, EPR, NMR spectrometer, I want excitation here at a high frequency, 400 megahertz. This is really, I think this is a good sweet spot right now if you want to use solid state sources. You can go higher, but the power drops off very rapidly. Although at 380 gigahertz, for example, you can get up to 100 milliwatt nowadays, and this will further increase. But for the time being, I think 263 gigahertz is a fantastic frequency to use solid state sources. I not only want continuous wave excitation, but I also want pulse excitation. I want to use arbitrary waveform generation here. I want to be able to do continuous wave detection of the EPR spectrum or time domain. Time domain is important if you want to, for example, study the relaxation behavior. Should be cost effective, compact, turnkey, and all sorts of samples I wanna look at. So the spectrometer itself, I'm not talking about the probes and how you couple the microwave into the sample, should all have like these kind of requirements. So why am I so why do I think that EPR is important even when you do DNP? Well, I am by nature a kind of an EPR spectroscopist, more that kind of wandered into the NMR land here. But I think it's very important if you want to optimize the DNP mechanism, if you want to understand the DNP mechanism further, if you want to create new polarizing agents, it's very important to understand the EPR spectrum, and not the EPR spectrum at 9 gigahertz, where it's easy to measure, where you can probably find every university will have somewhere kind of a expand CW spectrometer that you can study your sample at 9 gigahertz. No, you want to study it at the frequency where you do your DNP experiment. So the EPR is important to look at new polarizing agents, obtain relaxation properties, so T1, T2 times, characterize your saturation factor to see how efficient is actually your DNP effect. You want to measure the DNP enhancement profile to verify and also get to the optimum field positions. And sometimes you just want to look at the sample integrity. And what I mean by that is sometimes you look at transient radicals. That you have to make sure that you created them somewhere and then you put them in the NMR spectrometer, and then your DNP doesn't work and you wonder why. And the first thing you want to check is the radical actually still there? Or another important part is like look at the glass properties of your sample. We want a glass, but the glass has, you either have to go to a very certain temperature, you have to go to a low temperature, so that it's a rigid glass that you're looking at, and EPR can tell you immediately whether you have a rigid glass or not. There's a great tutorial, I think this is a few weeks ago, by Nino Willi about basics of EPR for NMR spectroscopists. So if you want to learn more about this, look at that tutorial. It gives you a great introduction into EPR spectroscopy. So I'll show quickly two examples here. On this here, this is it's a flavodoxin protein that we use the flavodoxin there as the polarizing agent, and that is a radical that is generated under anaerobic conditions. So I'm talking about protein sample injecting some reducing agent in the under a nitrogen atmosphere. We typically would do this in a glove box. We were not that fancy. It was more like a big bag that we used at this point. And then you want to freeze the sample very quickly also generating a glass at this point, and then study this for in DNP. So we can use here, this is a proton enhancement profile with this, using this flavodoxin polarizing agent. We can confirm this is the solid effect. We expected this, but this is also the EPR spectrum that shows us, all right, the line width is narrow enough that we have the solid effect here. There's actually also some overall effect going on here, but then this is well beyond this tutorial here. And if you look at glass properties, this is something that EPR spectroscopists, specifically high-field EPR spectroscopists, know for a long time. This is your typical tempo spectrum of, this is Fremy salt and glycerol water, but it's at 185 Kelvin. Kind of looks, yeah, it looks okay, the EPR spectrum. Not exactly like what you would expect, but this is just the EPR spectrum. But then when you look at the T1 relaxation times, you see this is not a flat line. There are these kind of dips in here, and that is indicative right away for some motion of the radical, the nitroxide in the sample, because we are at 185 Kelvin. And you can characterize the kind of the degree of freedom of the nitroxide by looking at these kind of relaxation profiles that you record at every field point across the EPR spectrum. So 185 is not maybe always the preferred temperature for DNP. We want to often go to the lowest temperature possible, but if you start experimenting around, you see like, okay, if I go up with the temperature, my enhancements go down, but there might be some transitions in, if you look at like proteins, there might be some temperature regimes you're interested in. You need to keep in mind that it's maybe your matrix softening up, and it's not a rigid glass anymore. And EPR spectroscopy can give you exactly this answer here. And also for like, if you look at paramagnetic metal ions as polarizing agents, that's the work of Björn Cotzelius and in his lab. I mean, you see all these wonderful EPR spectra. This is these are all recorded at 140 gigahertz, but you see of all these different polarizing agents. Here's manganese, gadolinium, BDPA, tempo, and those are the proton and carbon enhancement profiles. And when I looked at this figure, I was I saw, well, oh, okay, we have an EPR spectrum, that's great, and actually at 263 gigahertz. But when you look at this here, this is showing you the enhancement profile for protons, carbon, and nitrogen here, but the other part here is missing, because this is, again, because it's a superconducting magnet, you have a limited sweep width. With a frequency-agile system where you use the solid state source, now you can actually, you can sweep over the whole range here. You're not going to get the enhancements with the solid state source that you get with a Gyrotron, but that is beyond that's beyond the point. The idea here is to study new polarizing agents, optimize them, study relaxation properties and all that, and then go to use them in a high power setup. So I hope this is good motivation to kind of say like, okay, so now let's look at instrumentation. First thing is let's take a look at transmission lines here. Transmission lines can be as simple as an RF cable, coaxial cable, that you connect your probe to the source. You do this in an NMR spectrometer. Those are these black N-types cables, great, very flexible, low loss. These coaxial cables, they're typically all good to like 18, 30 gigahertz, sometimes higher. It depends on the connector, and there's a whole zoo of different connectors in there out there. So the N-types are the big ones that you use typically on an NMR probe, or you use a BNC connector. But then there are also the SMA, which get you up to 18 gigahertz, maybe 20, 28, and then higher frequencies. There are these 2.92 connectors, or 1.95 connectors. They become very fancy, but these cables also become very expensive. But at, I want to say, above 30, 40 gigahertz, they become also very lossy. And so coaxial cable is not really the kind of the transmission line that you want to use there anymore, the connection, so kind of transport the power. If you go to higher frequencies, you're gonna wander into like waveguide waveguide area. So most common waveguides are typically rectangular waveguides. If you do expand EPR spectroscopy, that's clunky thing where in CW your resonator is mounted on, but the losses in the waveguide, I mean, they are so low that often at the low frequencies, waveguide is still the way to go. If you're going for sensitivity and or like low losses, there's nothing that's going to beat a waveguide here. Sometimes you go to SMA cables, but that's more a convenience aspect rather than sensitivity. So if you go to higher frequencies, how do we get the power to the sample? We use, again, still rectangular waveguide. So there's like this, the long side is typically A and the short side is B. And if we look into this table here, so WR4 would be, for example, for 263 gigahertz, you see they become very small. So A is 43 mil, this is 21 mil, or for the rest of the world that is not thinking in imperial units, so it's like 1 millimeter by half a millimeter. So this becomes really small. And you see, if you look into 263 instrumentation, it will most of the time it will have WR4 waveguides, although the frequency range, let's say you're running already a little bit out of band here. You run like 1-2% out of band, because typically you would only use this to 260 gigahertz. However, the benefits to going to a smaller waveguide are not really that great, but or that justified. So it's okay to stay with a slightly bigger waveguide here. However, if you look into the losses over here, this is 0.0227 dB per millimeter. So that's 22.7 dB per meter. So at this high frequencies, waveguide is not really a good option. This is maybe okay to kind of plumb things around in your system, but you want to get as soon as possible. If you want to cover distance, you need to get to a different means of transportation. So here come the corrugated waveguides. Corrugated waveguides are typically cylindrical waveguides. They can be rectangular, but speaking of difficult, let's stick to the circular waveguides. They have these corrugations, and so these are these teeth here in that tube. I'm only showing half of it, so this is kind of, so you need to kind of mirror that in your mind here. So you have these tooth here. You can see them in here in this picture. This is a small section of waveguide to kind of connect from a horn to a sample here. These things can become very small. So at 285 gigahertz here, which is close enough to 263, we have like 300 microns, so 0.3 millimeter depth here. The width is 0.25 millimeters, and the porosity is like 0.5 millimeter. So those are small corrugations, really. But if you use these, you get really into this regime of like super, super low loss, 0.01 dB per meter. That's here. So we're way below that. That is fantastic. This is why these corrugated waveguides are so popular, to really ensure efficient microwave transmission from your source to your sample. And at 1/2 inch or 3/4 inch, which is almost 20 millimeters diameter, they are not that difficult to machine. And you can also think of, instead of really doing a corrugation, you can tap them. The performance is comparable to a corrugated waveguide. And the thing is, these waveguides come out of plasma fusion technology, and they're typically much bigger. So they're like 60, 70 millimeters in diameter. Because if you're sending like a megawatt of microwave power through this, if you lose 0.001 dB somewhere in a miter band where you go 90 degrees, that stuff gets hot. However, if you're using a 50-watt gyrotron, then anything below 0.01 dB is not really a concern anymore for losses. And there are many other areas in that, with alignment or coupling to the sample, where you have much higher losses than the straight sections for the waveguide. I need to say one thing here, that is, one piece of advice to keep in mind. These losses are only true for if you inject a pure mode into that. So now your solid state device actually will generate a very pure microwave mode inside that waveguide. Whereas a gyrotron, there will be coupling losses. If you have, you really have to make sure that the Gaussian beam that is launched from the gyrotron is as perfect as possible, so that you avoid these losses and don't have mode conversion in the transmission line. So now the corrugated waveguide is currently, I want to say, the go-to where you to connect your gyrotron source to the probe. But with there's actually a new area, not so new anymore, I want to say, but that people look into, and this is maybe not that there yet to be used, but it's something to keep an eye on, and that's 3D printed hollow fibers. There's still a lot to kind of optimize and to understand here, but these are hollow tubes, and these are Bragg reflectors. So you have like a your microwave travels in the middle here, but then you have these changes from like dielectric constants from like the polymer material that was printed to the air to polymer to air to polymer, and you can optimize that to make a very good reflector for a certain frequency. And here, this is 270 gigahertz. You see, this hollow fiber has 3 dB per meter loss. That's much less than the conventional rectangular waveguide. It's still 3 dB. 3 dB is still half the power that you're losing there, but it's also a meter. So for shorter sections, this is actually something really, I think, very interesting to keep an eye on. and it's fairly broadband here. The big disadvantage is the fibers are typically much larger in diameter. So you see this here is like easily like 30 millimeters in diameter. But if you have space, if you can afford it, then it's definitely something to keep an eye on. So with this, I would say if there are questions, we may want to get to them now, or we can do this later.
Yeah, we can start with a few questions. We already have a couple. I might let a little bit of time pass in case other people want to hop in with a few and hop in with one of my questions. This has been a very interesting first half already, Thorsten.
Thanks.
And not at all my wheelhouse in the slightest, so it's nice to see a little bit behind the curtain of what's going on. So you were mentioning the solid state source improvement. I was curious, with the recent improvements, has that been more centered around the diode design and like engineering within the source, or is it more related to not the materials being used to make the diodes? And kind of a follow-up to that is, where do you think is the kind of play space for the future of the solid state sources?
So I think the it's not. There is improvements to the semiconductor material that is used in there, but my understanding, what I have from like gained from discussions with VDI, it's really how efficiently do you get the heat out of the semiconductor. I mean, these diodes are very efficient in kind of the conversion from the low frequency to high frequency. But if you actually would look at the, this increases always, but there's a lot of heat that is produced. You pump in a lot of power in the low frequency side, and that needs to go somewhere. And that's the heat. So my understanding is that there are even like diamond substrates now used under the diodes to pull the heat out so that they survive, and that they also survive for a long time. I do have to say that so far our sources that I've worked with, so I have a 263 source from that is about 4 or 5 years ago, that produces 100 milliwatt, that still produces 100 milliwatt. And so the degradation over time is also very low. But it's this kind of engineering, like the thermal management to really get the heat out that makes this more efficient. Where is this going? I mean, I saw that I had a discussion with Terry Dubroca from the Magnet Lab in Tallahassee. They're looking into a 950 gigahertz EPR system. You have 5 milliwatt. I think it was 5 or 1 milliwatt. But that is a lot of power, and in a few years that will go up. Will go up further. Is at solid state sources for DNP? This is not gonna, you're not gonna wait for a long time to get like too much more power. But for like 263 gigahertz, I think that's a really good spot, and this will venture to 395 sooner or later. I'm pretty sure that's a 600 megahertz spectrometer. And then if you look at where is really the frequency where the bulk of people are doing experiments, not everybody has a 1.2 gigahertz spectrometer access to that.
Yeah.
Everybody would like to, but unfortunately it's not yet.
Agreed. All right, so let's go ahead and hit some of these other questions. We have first from Kamla on the sources portion of the talk as well. So which is the better DNP condition? Solid state source at 30 Kelvin or a gyrotron at 100 Kelvin in terms of cost and polarization enhancement?
Oh boy. I think you need to start your own matrix with what you want there. So at 30 Kelvin, you are, there's no, I can tell you already, there's no single answer to that. It's really what you're looking at, what you're trying to achieve there. If at 30 Kelvin, if you, you need to do helium spinning, so, or you do a static. So you can do static DNP. No? So all of the solution DNP is all done in static, starts with a static polarization. Now, if you want to add magic angle spinning, you can do 30 Kelvin magic angle spinning. Ken Thurber has shown that. This is like almost 10 years ago, even more than that. And you pay a lot of money for the liquid helium that you pour in there. However, Gail de Pape as well as Yo Matsuki have shown there are paths forward to for recirculation spinning systems. They go two different ways, but I do believe that at this point, it's sometime in the future, there could be really some viable technology coming out of that. So that cuts the cost down on the helium. If you want a workhorse spectrometer, a facility spectrometer, you're probably going to go with nitrogen cooling, and you pop in the sample, and that's a Gyrotron-based system. I mean, in terms of turnkey, that's the best you can have. The price you're paying is, if your DNP condition shifts a little bit, maybe you can still kind of catch it. But if it changes a lot, then retuning the magnet this is going to be a major thing. You know? So you don't want to do, you can't do like Monday, Wednesday, Friday, you look at nitroxides, and Tuesday and Thursday, you look at some gadolinium complex. So this is going to be difficult. Huh? So it's really like, it comes down, make your list of things that you want, and then see, and then decide what is the best technology.
All right. We'll do one more before we continue the talk, and then we'll address the rest of these questions at the end. But from an anonymous attendee, they're wondering, could you explain in simple terms how the corrugation helps to minimize the microwave power loss, and how the corrugation pitch is related to the wavelength?
So, as you said earlier, I'm a chemist. So I'm trying to explain that in the way I think about this. Maybe there are some microwave engineers that would now start cringing, but I think what it comes down to is the losses in the waveguides are always related to the currents that your electric field induce in the walls. So the corrugated waveguide does two things. First of all, you cannot, these losses that I showed you of 0.01 dB, those are for a 12 millimeter ID waveguide. And your wavelength at this point is 263. It's 1.14 millimeters. So you are by maybe a factor 10 overmoded. So the waveguide ID is factor 10 bigger than your wavelength. And so your electric field maximum is, first of all, it's far away from the walls. Now, the other thing is the corrugations help to cut down the electric currents that are in the wall. And so there is no really coupling of the electric field to the wall. And that's why the losses are so low. If you go to higher frequencies, So the corrugation relates to the wavelength. It's typically, I think it's a quarter wavelength. It's the depth of the corrugation, and then a third is about the of the wavelength is the tooth width and the gap width. So they're both roughly a third, and then it comes really down to you tweaking the corrugation parameters. Do you want the corrugation optimized for one frequency, or you saw this as kind of this U-shaped curve? If you do want to do like dual frequency operation, you can put the minimum in the middle and kind of use the same corrugation for two different frequencies. So it becomes a little bit tricky there. Or like you play around with these parameters and shape the curve. They are fairly broadband. I mean, you saw that it's like easily like 10, 20 gigahertz. You can you have negligible losses there. Yeah.
Thank you. Yeah, so let's go ahead and continue with the talk, and we'll get to these last few questions at the end. So.
Okay. All right. So so the next section is about how to build a DNP-NMR system, a spectrometer, and I go through like a couple of principles of how do you detect and how do you excite your sample. If you wonder in this area, I have to say that this cartoon is really kind of became kind of the story of my life at some point, because it's like, oh, you're so excited to building something, but most of the time this stuff doesn't work in the beginning, and then you just look through, like this here became kind of my mantra at some point, but you take the failure there is for me is my kind of motivation to figure out what's wrong there, why is this not working, and we need to get this to work. So let's look at simple spectrometer configurations. This is as simple as it can get. This is basically your setup for that you use in Gyrotron-based DNP right now. You have a source, you have a magnet, your sample here, you have a transmission line that connects your source to the sample. It's the most basic setup. There's no source protection here though. That's okay for a gyrotron. If you look into, if you watch Monica Blank's talk, they have this quality control where they put like a short, meaning a aluminum plate at the output of the gyrotron. They let this run for an hour, and that whole thing is stable and is really not acting up at all. That is impressive. However, for a solid state source, this is a very good idea. This is a very bad idea. You don't want to inject power back into the source. It becomes unstable. You're probably going to damage it, and depending on how much power you're reflecting back here. Now, the sample here, when it's not an EPR resonator, where when you're on resonant, you have maybe like minus 60 dB or minus 30, 40 dB reflection there, which is almost nothing. But this is just you have reflections from your coil, from your rotor, from your sample, from going from all these different dielectric constants. They all act as mirrors and kind of reflect back. Now, for a gyrotron, as I said, that's okay. Not so good for a solid state source. Now, what we're going to do? Well, if you're at low frequencies, you can just check out Fairview or Pasternak, the big distributors for microwave components, and you get an isolator, or sometimes it's called a uniline. So what that basically does is it only allows microwave to go in this direction and not in this direction. So it becomes kind of a one-way street here. And then there's some absorber integrated in there. And it's a very standard component. You can just buy this off the shelf. And depends a little bit on the frequency that you want, but up to like 20, 30 gigahertz, that is a standard component. And we want to go to high frequencies. So in this case, what we want is the isolator. If you dig into the microwave literature and kind of trying to understand how this device works, then you will very soon figure out, well, what that actually is what's called a circulator. So a circulator is a microwave device. It's a 3 or 4 port device which directs microwave in a certain direction. So here in this circulator, you just follow that counterclockwise rotation here. Everything that comes in here is directed here. Everything that comes in this port goes this way. Everything that goes from here goes there. But we put an absorber here so that we make sure that everything that is kind of reflected from the sample is going into the absorber. So I'm not telling you yet how this circulator is made or how we build this the circulator, but it's so that is a fundamental device in your spectrometer. So now you're looking at the this device and say, like, wait a minute, so now we're dumping everything in a load. Why are we not detecting that? So you can do that. So, and this is your basic setup of a reflection bridge. So you put a low noise amplifier here to kind of pull the signal out of the noise here, and then you put a detector here. And this works very well with if you have a resonator here where you basically have no reflected power, and only if you have absorption of the microwave, so it shifts a little bit the resonator condition, and then there's some power showing up here that you can detect here. But this system also, it operates on at the fundamental frequency. And what you can't get is you can't get the information between what is the absorption, what's the dispersion signal, so you don't have the phase information here. So to get but this is a very this is a very powerful setup already. For example, here, this is like in 2010, Ken Thurber, Rob Tycho, they published this paper about using the 30 milliwatt microwave source for DNP, and they're able to record an EPR spectrum already with this kind of setup. Now, if you want phase-sensitive detection, you need a reference arm. So basically what you do is you split your power into some reference signal here, and then you mix it with the signal that comes from your reflected signal from your sample. Now, what is this mixer device here? So the mixer is a 3-port device. It has an LO, a local port, an RF port, and an IF or intermediate frequency port. And as a 3-port device, it always has 2 input ports, 1 output port. And you can mix and choose here. So for example, you can down convert signals here. So this is your signal, you mix it, or this is your RF signal, you mix it with the LO, you end up at the IF. And if your LO and the RF is the same, then your IF is a DC. So if you see a DC signal, that means there's these 2 frequencies are the same. And then you can look at the power level, you sweep your magnetic field, you look at this at the power level there, and that gives you your EPR spectrum. You can also use the mixer as for up conversion. In this case, it's the intermediate frequency, and the local, the LO oscillator is the input port here, and your output is the RF frequency. There's, if you're interested, there's a whole zoo of different mixers that we can use. If you're interested in how they work, then you should definitely check out these tutorials by Markey Microwave. They're absolutely fantastic and very well written, from like beginner level to like super advanced level. So that is this magic mixer device here, and then we can look at the signal here. That's at DC level. We sweep the magnetic field. Or we can sweep the frequency here in the system too, given that all components are broadband and within the bandwidth. So this is called a Homodyne detection because your reference here and your signal path are at the same frequencies. And so it operates at a fundamental frequency, and this really has much higher already increased sensitivity than the setup, the very basic setup that I showed you before. Now we can add one more step to that, and that's the superheterodyne detection here. If you take a look at this, the blue stuff, the blue lines here are really at the high frequency. So this would be, for example, at the 263 gigahertz. This here is one of these AMCs, these multiplication chains. So for 263, you often have a multiplication factor of 24 that brings you into X-band territory. So we are here at like 10.5 gigahertz, something like this. Again, so this is your LO. You multiply this in this AMC, you irradiate your sample. So what is that here? So, or this here looks again something like a reference arm, what we saw earlier, but this is at the same frequency, and there's a mixer here. So I told you earlier that the mixer you can use an IF and an LO to kind of offset this this frequency. You just add it to that. So, and this is the purpose of this offset source here. For lack of a better name, I call this the offset source. So this is something maybe runs at 500 megahertz. So if you operate this at 500 megahertz, then here at this point, your LO frequency, that is like maybe here at 10 gigahertz or something like this, you create signal at 10.5 and 9.5 gigahertz, and then you can use a bandpass filter to get rid of one of the sidebands. But what's the advantage here? Why go through this ordeal? If you do that, then you can, in this section here, you convert your signal back from the high frequency to your intermediate frequency. It's offset by this frequency here, and then you can amplify, and you do a second down conversion step here with this with another mixer. The advantage is that here everything green and orange is all low frequency. It's all straightforward. And technology. So the really difficult part, you isolated to this part here, and also the low noise amplifier. It's always better to amplify at a higher frequency rather than DC for noise issues. This system here will give you the maximum sensitivity with this intermediate frequency arm. That is, by the way, it's a very general scheme here. This is how your NMR spectrometer works. It's exactly the same thing. Now, the other advantage is here that at this point here, the AMC will just basically amplify anything that you give it to the AMC. If you do CW input, you will get a CW signal output here. If you inject a pulse, it will upconvert the pulse, and you will get the pulse out here. If you put in a shaped pulse, you will get a shaped pulse out here. It might be not exactly the same shape that you put in there. It has something to do how these devices work, but you can tweak this to get the desired shape out of here. So the key becomes here. This is like the pulse is generated at a low frequency. So the key is here. So if we look at this a little bit more close look, so then you see at this point we can add what's called a pulse forming unit. And this pulse forming unit can have like pin switches, for example. Here you can have 2 pin switches here with a phase shift. For example, if this is a 180 degree shift here, you can do already some sort of an echo phase cycle sequence here. Or you can do you can use an IQ mixer that you drive with an arbitrary waveform generator, so you can create a shaped pulse here. Or this as an external input. Now, if you want to do Eldor, Deer, something like this, you can actually use that external input to inject another microwave. Again, this is all done at these low frequencies here. So there's a lot of technology available, and you don't need to deal with these high frequency, or you don't have to create the pulses at the high frequencies. In the future, I'm pretty sure with the availability of like digitizers that operate at higher and higher frequencies, there's actually a way you could just sample at this frequency. And I know that this was some effort for the Varian NMR spectrometers to kind of sample at the IF frequency. You don't mix down to DC anymore, but you sample your signal directly at these frequencies. This is possible because in the last 10 years or 15 years, these digitizers became faster and more affordable. Okay, so now let's talk about this device here, the circulator here. And that kind of now come to the last part of the talk, where we see like how do we build high frequency signal duplexers, and now we're wandering in the area of quasi-optics and Gaussian beams. Why quasi-optics? You may have heard that term already. If you look at high-field EPR papers, they always use quasi-optics there. The reason for that is, if you look at this, is a little bit more sophisticated now scheme of a dual frequency EPR spectrometer. This device here, if you want, if this is something you can buy for low frequencies, it's available at like a discrete microwave component. This is a discrete microwave component. That's a circulator. Again, works like whatever comes in here is thrown out here, what goes in here is thrown out here, and what goes in here is either directed to a load or back here. But so this is readily available at 95 gigahertz. If you go up, I think 130 is really the absolute maximum what you can find right now in circulators, like commercial circulators, not some device that some lab built. But it's like 95 gigahertz is really like the highest frequency right now, where you get these circulators. If you go higher, you need to think in a different way. So here come the quasi-optics. Quasi-optics is a concept in microwave technology for like high frequency radiation, or if you have even at 95 gigahertz, if you want very low losses, you use a Gaussian beam, you use a combination of mirrors and grids, and basically every discrete microwave component, like a circulator, there's a quasi-optical equivalent to that. So the quasi-optics uses a Gaussian beam here. So that is completely described by the radius of curvature. So at the exit here, it's flat. If you go further away, you have a phase front there, and the beam is expanding. How do you create these things? You have these launchers. Those are corrugated horns. I'll show you couple examples in a second. Again, corrugation here, right? They go from like half the wavelengths down to a quarter wavelength, so it's also a mode converter. And but the Gaussian beam is has some frequency dependence to it, like how the frequency expands here. So at low frequency, the beam expands faster. And at higher frequency, it actually kind of diverges less. That's something you need to consider when you start designing quasi-optics. It's basically the mirror size and gives you the lower limit of the frequency. Also, at every transition, HE11, that's the mode inside the launcher, or a corrugated waveguide, to TEM00, that's the Gaussian mode, that introduces 2% losses. There's nothing you can do about this. Well, there's a little bit you can do about this, but the horns that you're using, the standard horns, introduce 2% losses. So in your circulator device, you have the input port, 2% down. You go into your sample, 2% down. You come back from the sample, 2% loss. And then going to the detector, again, 2%. So it's just this cascading losses there that you just have to keep in mind. So how do they look like? This is a standard waveguide flange. There's this corrugation in here. They can be very short. This is a 95 gigahertz launcher. And the way we make them is there is an aluminum mandrel that go inside, and then you grow copper on that, and then you machine the outside, and then you put a nice gold plating on top of it. And so this is your typical Gaussian beam radiation profile, and people are very proud of how much that you achieve, like 99.95% Gaussian content in these radiation profiles. So then you propagate your beam through your quasi-optical components. So we have the launcher, as I showed you. Then we have mirrors. We don't use many lenses because they introduce losses. We use off-axis focusing mirrors, wire grids, and then wave plates. So types of mirrors that we're using are either flat mirrors, those are polished mirrors with like a gold-coated plate here, or focusing mirrors. So this is a flat mirror, this is a focusing mirror, that's a rooftop mirror, and you use these to refocus your Gaussian beam. This is just to redirect the beam by 90 degrees, and this is kind of a mirror that you use to reverse the beam propagation direction. We can use two different formalisms. One is ray propagation, that basically just tells you how much the beam diverges. And so here you see this is a lens equation, very standard lens equation here. The flat mirror just does divergence of the beam. And the Jones matrix formalism, they also tell us about the electric field polarization and how we change this. So a flat mirror, if the field polarization is up and you hit it this way, the field polarization will be still up. But if you have a vertical field, it reverses because of this -1 here. That's something to keep in mind. How do the grids work? This is a freestanding wire grid and has a spacing of 20 micron and a diameter of 10 microns. And depending on the orientation of the electric field, with respect to the wire direction, you either have the field transmitted or reflected. So although you can see through these things, actually, when you have them in the hand, you can just see through it. The electric fields can be reflected or transmitted. And then we can use this, for example, in a combination device like this here. That's a polarization transforming reflector, and so this is here a grid, and there's a flat mirror in the back. What you can do here, for example, you can, depending on that distance here, you can either change the polarization direction of the electric field, or you can go from circular to linear to circular to linear to elliptical to linear at 13 degrees, something like this. So it's a very flexible device. It converts your polarization and has very low insertion loss, and is designed as this compact half cube. Another element is this this Faraday rotator here. The Faraday rotator is a ceramic plate on this side here, and that's a combination here with a grid. And you see now already this is kind of a device that directs the beam in one direction, but the reflected beam is going in a different direction. So this can be at the heart of a duplexer. The insertion losses are generally a little higher because these plates here have a higher insertion loss of like 2 to 3 dB, and this per pass. So So now you have like a cheat sheet here, and that allows you kind of to lay out your quasi-optical components, the grids, the flat mirrors, refocusing mirrors, sources, detectors, all that here. This you can use for your for the design. Now, we always like to use what's called a Gaussian telescope, or in optics like 2F or 4F optics. We always like to use pairs of mirrors here. So, and we arrange them at a kind of a 2F distance. So that's the focal length. So these mirrors are identical, but because it's a Gaussian telescope, even if you sweep the frequency here, the beam waste and all that will not change. Here it becomes, this whole system becomes frequency independent. And what I mean with frequency independent means if your grids and you are operating at 200 gigahertz and 400 gigahertz, then this is a truly frequency independent systems. The only things that you need to change here are the horns that are launching the beam. Now, the mirrors are arranged in like always pairs of mirrors, and oops, going back. And so you need to be a little bit aware of that there is some distortion introduced, whether you go like this cis or this trans configuration. It's nothing new for the microwave technology experts, but in quasi-optics for EPR or magnetic resonance, people think of these components like as Lego, and you need to keep in mind that you may introduce a little bit of distortions here. So typically what you see like in the trans configuration, you see nice round beam. In a cis configuration, you can have this slight distortion. So I have a couple more slides and then I'm done here. So now let's start designing some quasi-optics. So what are the tools? You need your cheat sheet. And this is what I've kind of started doing over the last few years. I use a Sharpie and Post-it notes, square Post-it notes. I use a retractable Sharpie because for some reason I always lose that stupid cap. So that's a fantastic invention. And then you take your cheat sheet and write Post-it notes, and then this looks something like this. Here at home, I'm sitting there, and then this is a standard duplexer here for EPR that you can put together and make sure you have all the distances right, or this would be a power splitter here, or attenuator, sorry, that you can use for in a Gyrotron-based system, for example. So once you have all your Post-its kind of arranged and made sure that you think that the beam path and all this is all correct, we'll transfer that into a little bit more friendly representation here. So again, you see here, these are the mirrors, and we design the mirrors here that we have two cubes in between where we can put elements. So this is your source. You hit the mirror, and then 1, 2, mirror, and then to your sample. And then on the way back, there are two different modes of detection here. Whatever comes back from your sample, we have to make sure we can filter this out now with this Faraday rotator here. And again, 1, 2, mirror, and then 1, 3, 1, and then the detector. Or if we use a slightly different mode for detection, again, you see we hit the mirror here, 1, 2, mirror again, and then the detector. These are two different detection modes that are used in high field EPR. One is more sensitive than the other, but they both have their advantages and disadvantages. I'm not torturing you now to go through all these details, how this separation actually works, but it's based on the flipping of how you flip the beam polarization, because those are grids. And remember, if this perpendicular, it transmits. If it's parallel to the grid, it reflects. And this is exactly the kind of property that we're using here. We can also use the polarizing transforming mirror here, where we excite now with circular polarization. And remember, when you hit a mirror, it flips the polarization. So, for example, right hand is turned into left hand circular polarization, and the polarizing transforming mirror, then when it makes out of, let's say, vertical linear, it makes right hand polarization. When the beam comes back as left hand, it's horizontal. So then it can be transmitted through this path here and hit the detector. So this is a device. So in the previous slide, I showed you using the Faraday rotator. This is the device to use the PTR. We can also build beam manipulators. So this would be kind of a attenuator and use a universal polarizer. So this is your transmission line. You can add this in here and regulate the power, but also change the polarization, for example, here. Or this is a device which is a beam splitter. So if you have a lot of power coming in here, for example, from a gyrotron, you can direct some of the power to this output and some of this power to this output here. So in the last few slides, I just want to go over and just show you a couple of systems so that you get kind of an idea how big they are. Quasi-optics can be quite big. This is the Magnet Lab. It's a 95 gigahertz EPR spectrometer. This is a system operating at about 200 gigahertz in Songhi Han's lab. The quasi-optics is all up here, and all the other electronics is located down here. This is the magnet. This is the system that Rob Tycho uses and can further with like this low power solid state source. And so you irradiate here. I believe this is the Faraday rotator. Here's a mirror that shoots up the beam into the magnet, and whatever is reflected comes back and then is detected here. You can, so these are systems. This is a pure EPR system. This is EPR DNP, and this is DNP EPR system, I would probably call it this way. You can also use quasi-optics, for example, here in this Warwick setup, to transmit your power from the gyrotron over long range down here in this magnet. And you see you have this train of mirrors that you go down. And this is, I've seen this here. This is, I want to say this is like 3 or 5 meters distance here. Here is another device where you can change linear polarization to circular polarization. That's called a Martin-Puplet interferometer. It's a little bigger device. It does the same thing as what the PTR does, but it occupies 9 cubes rather than 1 cube. This is at the Magnet Lab, the beam splitter, what I showed you like just on an outline in the previous slide. So that is actually a beam splitter at 395 gigahertz for 600 megahertz NMR that is operated at the Magnet Lab. And here are a couple of our devices. Was like an early prototype. You see our quasi-optics are smaller. We use now a 2.5 inch by 2.5 inch cube size. And so this whole system here fits in this little box. This is a system that is used for polarized targets at the University of Hampshire. In New Hampshire, this is a system at 263 gigahertz. And showing like, okay, if you sweep the field or the frequency, you still get the same EPR signal. This is something you need to convince the EPR spectroscopists about. That's the same. With this, I stop. A couple more slides. This here, I don't expect you to read this right now, but I put down a list of references that I think are always helping me every day. I'm looking at least one of these papers or books here. And There are a lot of people that have worked on this, and collaborators and friends, and discussing things specifically for quasi-optics. Here I want to point out Songi's lab and Ilya. It's a fantastic source of inspiration. And there are many other people involved in certain different stages. I want to do one thing. So if you know New Melanie, and it's a terrible disease that she died of, and so there is a fund by the Dana-Farber Jimmy Fund, Dana-Farber Institute, the Jimmy Fund. If you want to donate that, or if you just want to know a little bit about her, there's this page to go to. So you can learn a little bit about Melanie, and see the wonderful contributions to that, to fight that disease. With this, I want to thank you, everybody. If you have more questions afterwards, feel free to email me, feel free to message me on Twitter, and ask questions.
Thank you, Thorsten. It's a very nice talk, and thank you also for bringing up Melanie. I know that she'll be greatly missed by the community. I know we've gone a little bit long today, but I think it was well worth it. I think a lot of people got a lot out of this talk. I know I did for sure. I had a couple of flashbacks to optical spectroscopy near the end back there. Apologies to any students whose professors missed class while they were here, but please feel free to throw any questions into the Q&A, and keep an eye out for word from our Twitter account, and of course through the email list at MIT. We'll be giving out more information come around January when we are back into our full swing. But as far as questions for Thorsten, we have a couple from earlier that I'll start out with. Thierry Broca, he mentioned thank you for the talk, and that you had mentioned the 3D printed waveguide. And do you see this being used in the probe and maybe in a horn shape to focus the beam on the sample to then improve the B1 field?
I think there needs to be a little bit more research in the type of material that you use, because you can, I look at this, I can tell you that is the gray resin from the Formlabs printer. I think we need to, or the community needs to play around a little bit more with the resins to optimize this. But yes, horns, all sorts of shapes to get into awkward places in your probe. I think that is exactly where this will be going. Also, you need to think about a little bit like when you want to do this, cool this down. So what's happening there? How many thermocycles you can go to? But this becomes so cheap. So that, I mean, if you look at Zender Barnes' magic angle spinning spheres, I mean, he has this crazy slide with like, is it like 100 or 500 status that they printed? Yeah, so you just go through this and play. I think this is a great area to play right now.
And then Eric Yuan has a question. Says, a stupid question perhaps, but I've heard that in the fields like 5G communication, we can amplify the signal nearly as high as we want. I'm wondering if there are different limitations for several hundred gigahertz amplifiers.
So first of all, I would say 5G technology is fantastic for EPR spectroscopy, because the frequency regime, there's like the higher frequency, the backhaul frequencies, where there's a lot of progress, but in Q-band, like 28, 30 gigahertz is fantastic what you see coming out from 5G there. And I think this will also lead to further kind of smaller spectrometers and all that. That's fantastic. So, I mean, the X-band EPR was riding on the radar wave from like after the Second World War, and now I think for Q-band we will ride on the 5G wave for a long time. I do think that even at higher hundreds of gigahertz, again, this is technology you need to get better thermal control in your devices. The better you are there, then the better, more power you will get out there. There's probably maybe some limit to this, but I don't notice. So, but I do think there will be more power coming out of this solid state devices in the future. I mean, for me, it's like my experiences, every time I talk to VDI, they add 10 milliwatt more, depending on how long you wait until you talk to them again.
All right, so our next question comes from Blake Wilson, asking, what are the frequency limits for the quasi-optical Faraday rotators? And what materials can be used for greater than 300 gigahertz?
So I would say in general, so quasi-optics, the way you need to think about that is, I showed you the beam expands after it leaves the launcher. So now you need to make sure that your mirror surface is big enough compared to the beam waist. So we typically go for like something like 4 times the beam waist is the mirror surface that we want, and that gets you down to your cutoff is something at like, I think minus 30 dB or something like this. So it's really like all the way down there. Yeah. Now that's the mirror, and that sets the lowest frequency of the system, and then how many cubes you go between mirrors, but this is something you can adjust. You can go 3, you can do 2, but most of the time you want 2 at least to get some elements in between. For the Faraday rotator, the way the Faraday rotator is made, it's a kind of a dielectric material that gets poled in a pulsed high magnetic field. And it depends on the travel length through the material. And so at low frequencies where you are at like a 263 gigahertz, you have 1.14 millimeter wavelength. So your material is given by that wavelength. If you go to higher frequencies, it becomes more difficult to machine exact this thickness. And so I do think that at the higher frequency, the polarizing transforming mirror, where it comes down to, you need to make sure that the grid and the mirror is like really parallel, but then this position movement, you can do this very, very accurately. So I think that the PTR at higher frequencies there are some advantages to them rather than the Faraday rotator plate.
Right. And then our next question comes from Kong, saying, for one, great talk. And then you mentioned that it is important to measure T1 and T2 of the electron. Can you describe how does your setup measure them specifically? And secondly, is it possible to use the field modulation technique plus a lock-in amplifier for EPR detection at high field?
So I didn't go into these details. So the way we set up these systems is the CW detection is always possible. I mean, that is basically the simplest detection. You use a field modulation. It's standard EPR. You do field modulation. You can either sweep the microwave frequency, or if you throw in a small coil, then you sweep the additional coil, and then you use a lock-in amplifier to pull the signal out of the noise. That works. That always works. You can, for pulsed measurements, it's a standard pulsed spectrometer, what this setup is. If you add the pulse forming unit, then you can create 90, 180-degree pulses. You can move them. You have a digitizer. So it becomes a little bit more demanding in terms of the technology that you need for, like, you need a pulse generator, you need a digitizer, all this. But this is, there's no rocket science there anymore nowadays. This is you can go very simple with, I mean, very simple or low resolution techniques to go all out to key sites and look at the fancy AWGs that they have, and so this is. I didn't explain these different options there. It's like now the excitation, how you control this pulse forming unit and the digitizer. There's more equipment needed at this point. I also want to say that we use SpecMan extensively for these systems. So there's no LabVIEW programming or whatever. Yeah, so I've done that. And I don't want to do that anymore. But it's a proper software where you basically you create your pulse sequence and then do your pulse experiments or CW experiment.
All right. So then we have a follow-up question, or I guess I think it's getting a little bit scrambled. Question from an anonymous attendee. For an EPR perspective, you mentioned the upscaling of the pulse by a TWT. What are the limitations on upscaling it?
Not sure if so TWTs are in EPR typically used at X-band or Q-band frequencies. Your amplifier to generate the power pulses is always operating at the spectroscopy frequency where you want to do the spectroscopy. So you can have TWTs at higher frequencies. I think the highest I'm aware of right now is like something like 250 gigahertz, 5 watts, something around there. But these are also devices that I want to say that this is not an off-the-shelf device. I don't know a Q-band TWT how much off the shelf that is, but I mean there are vendors where you can buy them, but the TWTs become a little bit more experimental when you go really to really high frequencies. Also keep in mind that the TWT is what's called a slow wave device, and so they have structures in there on the order of the wavelength. And there's a very high power electron beam going through, and they degrade over time. So with that's again, so with solid state devices, they degrade because of the heat that you need to pull out. The TWTs and also the EIKs, they degrade because your electron beam hits something on your resonance structure in there over time, and then they degrade. That's the great thing with the Gyrotron. The Gyrotron has a beam that goes through an overmoded cavity that once everything is aligned, this thing's gonna work, maybe not forever, but close to forever. Yeah. So and there's no issues over time of the actual Gyrotron tube. Yes, there can always be a power supply breaking or the cooling water not running or something like this. Yeah. So, but there are TWTs have a limited lifetimes. Gyrotrons, I don't think that we're gonna see, unless there's something wrong with the Gyrotron, they will work for a long time.
All right. So our next question we have from John Blanchard saying, almost certainly a dumb question about thermal management. Is there a reason not to just dump all of the microwave equipment in liquid nitrogen, some other microwave transparent liquid if necessary?
I was actually thinking about exactly the same thing when I was explaining the thermal management. I don't know. And I don't think it's a dumb question, but I'm the wrong person to be asked for this. I would direct that question to Jeffrey Hessler or so from VDI and see if this is a possibility. I honestly I don't know.
Certainly the NMR spectroscopist way of thinking. It's, well, what if we could just put it in some liquid?
Exactly. Yeah.
Oh,
fantastic.
All right. And then our final question for the time being is from another anonymous attendee saying, how far are we from a commercial frequency agile gyrotron like Alexander Barnes is?
If we have enough customers and people that are interested in that, it is definitely something to look at. I would like to see, and I'm certain in the next few years or maybe even the next few months, we'll see more publications coming out of this lab, and really see the advantage that technology provides. There is another. This is when you use the Gyrotron as an oscillator, basic. So you switch it on, and the microwave comes out there. We are working also on amplifier, Gyrotron amplifier at 395 gigahertz. That is a more flexible device. However, that's a research project. This is for a commercial product. I think that's time will tell. But this can go anyway. I mean, there are demonstrated gyro amplifiers even by the MIT group, but gyro amplifier is also like in radar technology. That's nothing new there. So they are around for a long time, but showing all the benefits for DNP spectroscopy, and then also talking about pulse DNP. This is there's still a lot to show and to make a good case for the benefits, that this is the way to go. Yeah? Because these devices are not going to be cheap.
Yeah. And found ourselves another question from Frederick Mentik asking, is a frequency agile second harmonic gyrotron harder to design?
Okay. It's harder than the fundamental mode gyrotron. Yes. Is it impossible? No, I don't think so. I think that's a good question. But everybody who would start with this is probably well advised to first start with the fundamental one and then go to the second harmonic. But I don't see a reason why this shouldn't be possible.